Alright, so now that we are done with our thermodynamics unit, we are now going to apply those principles of energy changes in systems and surroundings to the atom. Now, we've already discussed a little bit about the basic structure of atoms, but now we're going to get into the modern atomic theory of atoms. This is the more complex stuff, but it's also the cool stuff when it comes to atoms and more the modern idea and look at what we believe the atom is. So to start out with, lecture 1, we're going to look at this word called relative atomic mass, and we're going to learn to solve problems related to the relative atomic mass in this particular unit. So looking at the essential questions for the unit, again, these questions are questions that you need to be able to answer for the quiz in class as well as on the test. So after this lecture, you should be able to know how a mass spectrometer works. This is really important. There are several steps or series that you're going to have to learn, just basically memorize how a mass spectrometer works. The other essential question is, how do I use mass spectrometer data to calculate the relative atomic mass? And we'll go through that in the calculations here in this tutorial. And then the last one is, how are the masses on the periodic table determined? And that ties in with our second essential question that we'll look at. Alright, so our first question in our lecture handout notes deals with the idea of what is a mass spectrometer. And so what we're going to do is we're going to keep this as basic and simple as possible. But a mass spectrometer is an instrument or a device that can give us some powerful information about the isotopes of different elements. And so let's kind of write this down in our notes here under what is a mass spectrometer. And essentially, the masses of each or of the different isotopes and their relative abundance can be measured. Using a mass spectrometer. Okay, so the key words here are, we can figure out the masses and the relative abundance of the isotopes that make up an atom using a mass spectrometer. And with this data, the relative abundance and masses, we can actually calculate what is known as the relative atomic mass, which we'll define a little bit more here later. Before we can define relative atomic mass and actually calculate it, we need to know how the mass spectrometer works, or the specific steps that are related to the mass spectrometer. And so that's what we're going to do. We're going to write these steps down. If you look at your notes on question number 2, it says, what are the basic operations of the mass spectrometer? And you have several steps: the vaporization step, ionization step, acceleration, deflection, and detection. And all of those steps you need to know very well. You have to have them down for the quiz, so make sure you memorize them. So let's go through each one of these steps to make sure that you become familiar with it. with these. Now, those of you that have the IB book, in your chapter 2 on atomic structure in section 2.2, you can get into the IB book and they will list the steps of a mass spectrometer that we're going to go through here. But we're going to do it here, so you may not have to really go back and refer to it. Alright, so step 1 is the vaporization step. Alright, so what occurs in this step is seriously, just as it says, the individual atoms are going to be converted into a gas state. So the atoms are basically vaporized. Okay, or in other words, they become a gas. All the elements have to go into a gas. Okay. Now the next step is the ionization step. Now what's going to occur here is that the isotopes of the element, whatever we're looking at, is going to become ionized, meaning that they are going to lose electrons in their outermost shell and they're going to become positively charged. So the atoms are hit with high energy electrons. And that's going to knock out electrons from the outer shell of these atoms, and thus producing positively charged ions. Right? So you can kind of think of it, you have this vaporized gas, all these atoms are vaporized. You're going to take high energy electrons and they're going to smash into these atoms, and that's going to cause some of the electrons in the outer shell, so those valence electrons, to actually eject, or what we call being ionized, and this is going to produce positively charged ions. So when we erase this and when we draw kind of a diagram of what that would kind of look like if it was like an equation or something like that. So you can see that we have X is going to represent some element or some atom, and of course it's going to be in the gas state because of the first step. And we're going to take a high energy electron and we're going to crash it into that atom, and it's going to cause the other electrons, the valence electrons, to be ejected, forming a positively charged ion, which is also still in the gas state, plus you're going to get the 2 electrons out of here. One of those electrons that we get out, let me erase that and make that a little bit better. So 2 electrons. You're going to get the 1 electron out of there that we actually added to eject the electron in the first place, and then the other electron is the one being ejected, so you get 2 total electrons out of here. Alright? So this is essentially the equation to represent the second step of creating basically positive charged ions through the process of ionization. So make sure you're aware of that. Right, so let's go ahead and go to the next one. So I'm going to erase all of this. The next step, which is known as the acceleration step. And so we can get this, and then I'll write down that step for us. Alright, so acceleration. Okay, what's going to happen on this is now we have the positive ions are now going to be attracted to negatively charged plates. This attraction, then, these positive ions that are attracted to these negatively charged plates are going to cause these ions to accelerate. So ions accelerate or ions accelerated by an electric field then. Alright, they're excited, or these electrons are attracted to the charged plates. They're going to cause those ions to accelerate through that electric field and speed up. Right? Right, so then the next step, after those ions that are positively charged, that are in the gas state, that are accelerating through that electric field now there's going to become a deflection period, or deflection step. Now this takes a little bit more thinking here on the deflection step. Basically, it's the deflection step that's required is going to be when the different isotopes of an element are actually going to be separated, and so that we can analyze the different isotopes by themselves in this deflection step. So they're basically going to be deflected. We could say now the accelerated positively charged or positive ions are deflected. Now, the amount of deflection. Okay, so they're accelerating. They're positive ions. They're going to be deflected. So how do we know how much deflection is going to occur? Well, the amount of deflection depends on the charge-mass ratio. So the amount of deflection is proportional to the mass charge. Actually, I should say charge mass ratio. That would be better. Charge. slash mass ratio. Okay, so make sure you write this down, and then let me kind of further explain what this all means as far as the mass charge ratio is concerned here. Alright, let me just erase this. And then let me define the mass charge ratio a little bit more. When we're talking about mass, is the smaller. So in other words, the ions with a smaller mass are going to be deflected more than heavier ions. Okay, so the smaller the mass, the more they're going to be deflected, and that's something make sure you understand. This is an important point as far as the mass is concerned with the deflection part. Now, as far as charge goes, is ions, and this is also really important, ions with higher charge are deflected more. So the more charge they have, the more deflection is going to be occurred. And so basically this will determine the mass charge ratio and how much deflection they'll be looking at. So we're looking at their charge plus their mass, and so therefore the smaller the mass, the higher the charge, the more deflection that will be occurred when separating these ions. Okay, so just make sure you have those 2 points down with mass charge ratio and deflection. Okay, let's go to the last step, and that is the detection step. And this is pretty easy to understand. That basically that detection step this is basically after the deflected ions, they're going to send a signal. Okay, so the charge mass ratio is detected, and a signal is sent to a recorder. Right, and the recorder is going to basically shoot out a specifically a graph that's going to show the mass charge and the percent abundant of each of the isotopes that is in that element. And so this graph is called a mass spectrum. Okay. And that's just the graph of the mass charge ratio and the percent abundance. And we're going to look at one of those here in just a second. Alright, so these are the steps to the mass spectrometer and how it works to create information that we can eventually use to calculate the basically the relative atomic masses of elements. Alright, So make sure you understand what a mass spectrometer is in these steps. Alright, let's go on. This is a diagram that's in your notes, and it basically shows the diagram of a mass spectrometer and the different places where you see we see ionization, where you see ionization that occurs. There's ionization, the acceleration step, the deflection process, and the detection where each one of these occurs. Again, you don't need to diagram this, you just need to be able to know what these steps are. Alright, this next slide is going to show us an actual mass spectrum, or a mass spectrometer spectrum here. Let me write this down so you can look at this. Mass spectrum. Now, this mass spectrum data is really important because it is from this spectrum that we can calculate the relative atomic mass. And so actually we need to look at that definition. So let me go back one slide and let's define relative atomic mass for you. And this would be question number 3 in your notes, is what is the relative atomic mass of the atom? This definition I want you to know. Memorize it, know it for the test and the quiz. Both AP and IB has often asked to define what the relative atomic mass is on the AP and IB exam. Okay, so here it is. Essentially, it's the average mass of an atom of the element taking into account all its isotopes. And their relative abundance. Compared, and this is important, make sure you add this to your definition, compared to one atom of carbon-12. Carbon-12. Okay, so there's the definition. The average mass of an atom, of an element, taking into account all of its isotopes and their relative abundance, and is compared to one atom of carbon-12. Now, why do we use carbon-12? Well, carbon-12, we're going to say, so carbon-12, we're going to say has a relative, or exactly, a relative mass exactly of 12.000 AMUs. Okay, so it has 12.00 AMUs exactly. And again, AMUs, if you remember, stands for atomic mass units. AMUs, atomic mass units. And so we choose carbon-12 as our comparison of other elements in their relative masses. Basically, carbon-12 is very common. It's easy to transport and store, and it's a solid. And so in 1961, I believe, is when they decided to use carbon-12 as their comparison to the average masses of of the other atoms of different elements. All right. So let's go back to our mass spectrum slide here. And let's show you how we can use the mass spectrum to calculate the relative atomic masses of these different elements. So the graph here on the x-axis, you're always going to have the mass-charge ratio. And on the y-axis, you're always going to have the percent abundance recorded. And of course, this is the detection part of the mass spectrometer to record this data. So this shows us the data for magnesium, and you can see that magnesium has three isotopes of magnesium. Magnesium 24, magnesium 25, and magnesium 26. And this data here is going to show us basically not only the relative isotomic mass, but also the percent abundance of each one of these isotopes. How often these elements occur, or these isotopes, these atoms, these isotopes occur in nature. And so you can see here that with magnesium 24, if you look up in this table here, magnesium 24 has a percent abundance of 78.99%. So it's basically most of the element magnesium is made up of magnesium 24 isotope. Magnesium 25 is only 10% found in nature, and magnesium 26, 11% found in nature. And so now we're going to use these numbers to actually calculate the relative atomic mass that is found on the periodic table of magnesium. So if you pause this, take out a periodic table and look at the element magnesium, you're going to find that on the periodic table it should say roughly have a relative atomic mass of 24.32 AMUs. Alright, so what we're going to do is we're going to learn how to calculate this number for every single element on the periodic table using the mass spectrum data given to us. And you're going to have to do this on the test. And so this is how you do it. The first thing you're going to do is you're going to take the relative atomic mass of magnesium, which is relative isotonic mass of magnesium 24. Let's write this down. So 24, and you're going to multiply it by the percent abundance, 78. Let me actually try to erase this and get more room here. So we're going to go 24, and you're going to multiply that by 78.99, and you're going to take 25 times 10.00. So you're taking each of the masses of the isotopes, and you're going to multiply by its abundance. So 26 times 11.01. Now this should be a 1895.76, and this should be 250.00, and this should be 286.76. Then what you're going to do is you're going to add those together. You're going to add all three of those numbers together, and you're going to get 2432.02. And you're going to divide that number by 100, since these are based on percentages. And when you divide that by 100, you should get an answer. Let's put that up here. This answer, after you divide, should be 24 0.32 AMUs, which matches our relative atomic mass that's on the periodic table. And so this is how we calculate not only the relative atomic mass, but the masses that are on the periodic table that we use for each of those atoms. And so again, all we need to do is take the mass of each of the isotopes, multiply it by its percent abundance, and then we add them together, those numbers, divide by 100, and that will give us the relative atomic mass. You need to be able to do this calculation for the quiz that we take in class on this lecture. Alright? Okay, this is all that we're going to cover for today in this lecture. Make sure that you go back and review this lecture if you need to. Look at your notes, look at the essential questions, study those, and prepare for the quiz. And that is all.